we're going to imagine that we drop a ball from some high distance, like say a tree in your backyard. And we want to know if it falls some distance delta x, or really displacement delta x, how fast is it going right before it hits the ground? Normally the way we would do this is a two-step way, but what we're going to do is derive an expression which allows us to get that velocity given this displacement delta x. And so how we're going to do that is we're going to use two of the equations from...
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Welcome back to Lecture 3. This lecture is titled Rates of Change. And the rates of change that we're going to talk about are probably familiar to you. The first one is speed. Now, speed is very simple. It's the distance traveled divided by the time taken. You're probably familiar with this if you've ever gone for a trip in a car. You might travel at 60 miles per hour. That's roughly 1 mile, exactly 1 mile per second. That tells you how far you go per unit of time. So if you've traveled for, say, 100 seconds, how far have you gone? If you're going 60 miles per second, 60 miles per hour. If you've traveled for 1 hour, how far have you gone? You've gone 60 miles. If you travel for 2 hours, you've gone 120 miles. So the formula for that is just distance traveled divided by time taken. Now, velocity, to contrast that, and we'll talk more about the vector quality of velocity in a later lecture, okay? But velocity is a vector. So in this case, direction makes a difference. So my speed might be 60 miles per hour, but my velocity could be something like 60 miles per hour north. That means I'm traveling in the north direction. Now, if we restrict ourselves to one dimension, then we would say that we've got a positive direction and a negative direction. The negative direction would be going backwards. So if this is my reference frame, or my ruler really, right? If I'm going with a positive velocity, I'm going this way. If I'm going with a negative velocity, I'm going backwards, like this. Now, why is this important? Well, it's not distance traveled that's important with velocity, it's actually displacement. And so it's the displacement divided by the time taken. Now, if we're only traveling in one direction, that's not going to make much difference. So if at time t equals 0, I start driving, and I drive at 60 miles per hour for 1 hour, always in the forward direction, then the speed will be 60 miles per hour. The velocity will be plus 60 miles per hour. However, if I drive for 1 hour, and then I turn around, let's assume instantly, and drive all the way back home, my distance traveled will be 120 miles. I add the two paths, even though one of them is going in the backwards direction. And I divided by the time taken, so let's say 2 hours. So I went 60 miles per hour in both directions, so my speed is 60 miles per hour. But my velocity will actually be 0. And the reason why is because displacement is a measure of how far you are from some reference point. And so that brings up the notion of a reference frame. And I don't have a lot of room here, I'll draw it right here. So if I draw a two-dimensional graph, with the x-axis being t, time, and the y-axis being x. I know that's confusing, but this is kind of standard the way that we do it. Call this distance. All right, so this is 0, x, and this is some positive value of x. I could allow for a negative value of x by extending the axis below here. There's no reason to do a negative value of time unless you're trying to track something that occurred before you started your timer. But we'll ignore that case for here. So if I travel at 60 miles per hour, that means that at 1 hour, let's say that 1 hour is here, and this is 60 miles, 1 hour, then this point here would be my final destination. And we would have a line, which is going to change when it goes, extending up to that. And then the return trip, I would be going backwards, presumably at the same rate. Extend that out just a little bit more. And here I am back home. So my total displacement, right, is my kind of, usually the way we write this is delta x, where delta tells us that we're looking at a change. And so delta x would be kind of the x final minus the x initial. Whereas, and that's what we'd use in velocity. So velocity is going to be delta x divided by delta t. So time taken is a time interval, and we call that delta t. So my displacement, x final, well, it's 0, and my initial position is 0. So this is just equal to 0 divided by 2 hours, which is, of course, a velocity of 0. And that's because of the vector nature of velocity. The speed, however, is the distance traveled. Well, I traveled 60 miles, and then I traveled another 60 miles. Now, even though I traveled in the opposite direction, I still have a total of 120 miles that I've traveled. So I have 120 miles divided by the time taken, which we presume is 2 hours. So if this is at 2, then our speed would be 120 miles divided by 2 hours, which is, of course, 60 miles per hour. Whereas this one was 0 miles divided by 2 hours, which is 0 miles per hour. Now, I should point out that I say speed and velocity. What I really mean is average speed and average velocity. And the reason it's an average is because it's taken over this large interval. Instantaneous speed, that's the speed that we mean when we talk about a much smaller interval. In fact, we talk about an infinitely small interval. So if I were to look at how fast am I going right here, at that point right there, well, I can imagine, blowing this region up and considering an interval, say, started here, stop it there. And you can see that I've got, a delta t here and a delta x here. And I can take that as my measurement of the average velocity. But if it's really small enough, I can call it the instantaneous velocity, especially if the time interval over which I'm measuring is at kind of the limit of what I can measure. So in your automobile, for example, when you look at your speedometer, it says you're going 55 or 60 miles per hour. And the way it knows that is it's tracking how long it takes for the wheel to make a revolution. And so, the distance that a wheel travels to make one revolution is not that far, so it doesn't take that long. And so that is pretty close to your average velocity, or average speed, rather. Oh, I erased the title. Rates of change. So, when we look at this graph a little more carefully and point out something that's interesting, or that should be familiar to you, which is that if I'm traveling at a constant speed or a constant velocity, and let's say that I've got some points here, 1, 2, 3, we're going to make this 10, 20, 30, and let's say that after 1 second I traveled 10, we'll make these meters. And then after 2 seconds, I had traveled 20 meters, and after 3 seconds, I had traveled 30 meters. And we make, we graph this. We use a straight edge here to get the line we're looking for here. We'll see that this is in fact a line, and the velocity, or the average speed, is the slope of this line. So we think of the measurement starting here at t equals 0 and going all the way to the end at t equals 3, we would get the average velocity there, which I'm just going to write v sub avg, is equal to, well, that's 30 meters minus 0 meters, because that's where we started with 0, divided by 3 seconds, or that's pretty quick, but fine, 3 seconds minus 0 seconds. And that gives me 30 meters divided by 3 seconds equals 10 meters per second. And the rise over the run, you'll recall, is the slope of the line. Right? The standard form of the line, we say slope-intercept form, is y equals mx plus b. I'm just going to change the variables to match what we have here. I'm going to say that it's equal to x equals mt plus b. B is the y-intercept, or in this case, the x-intercept, where it intercepts the x-axis, and that's at 0. Right? So in our case, this goes to 0, and we're left with just x equals mt, where m is the slope of this line, and that's the rise over the run. if I were to look at the interval between, say, 1 second and 3 seconds, that's a smaller interval. Right? It's going to look something like this. In this case, the average velocity would be 30 meters minus, at 1 second, it's at 10 meters, divided by 3 seconds minus 1 second equals 30 minus 10 is 20 meters divided by 3 minus 1 is 2 seconds, which is still 10 meters per second. That's because we're traveling at a constant velocity. And so we get a straight line for our position curve. And straight lines only have one slope. So in this case, the instantaneous velocity is the average velocity. And so that's kind of handy in cases like this, where we're traveling at a constant speed or velocity. One final thing I want to mention regarding these rates of change and these reference frames is that reference frames are just that. They're frames of reference from which you measure. And you can have more than one. And the important point here is that there's no such thing as an absolute velocity. Only a relative velocity. So that's your speed as measured relative to some reference frame. I'm standing still currently, but I'm on the Earth, and the Earth is rotating around the sun, I think, like 60,000 miles per hour. I think that's possible. I think that may be the number. And so the sun is probably moving about through our galaxy, and our galaxy is moving about through our universe. And so there is no absolute reference frame for measuring velocity. What if I have two reference frames? What if I had a train like this, and on this train we have a guy, and he's standing still, and he's got his own rulers here. So we could have a ruler on this train, and then there's a guy standing on the side of the tracks here, watching the train go by. Let's assume the train is going in this direction with some velocity. We'll just call it V sub s, or wait, I'm sorry, V sub t for velocity of the train. Now, if I look at the position of some object, say this here, and this guy has his own reference frame, and we're going to synchronize these reference frames such that when these two guys were lined up here, we'll call that t equals 0, and we'll say that the zeros of their rulers were lined up at that moment right there. So just as they pass each other, we'll set our stopwatch for the purpose of measuring time intervals, and our rulers will be aligned at that moment. At a later time, however, this guy's going to move on down the track. So if he sees, say, a ball on the side of the track, he might measure it at, let's see, it's 1, 2, 3, 4, 5. But the guy on the track itself, right, that's not moving like the train is, might see it at 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So this guy sees it at 5. This guy sees it at 9. In physics, we work with problems like this all the time. We have to look at two different reference frames and translate from one reference frame to the other reference frame. So if I want to ask about the velocity of this ball, let's say this ball is moving with a velocity v sub b, okay? And we'll just let this be, I don't know, 1 meter per second. We'll say the train is going, well, use 10 meters per second, since that was our previous velocity. The guy on the tracks, right, he of course sees this as moving at 1 meter per second. That's the speed in his reference frame. That's what I meant by saying the ball is going at 1 meter per second. The guy on the train, however, is going to see it at a slower speed because he's moving in the same direction as the ball. And there's a formula you can use to kind of translate between these, and it's pretty straightforward. It says that the velocity, say the prime, the moving reference frame, okay? That'll be this one up here, so v prime is equal to the velocity in the unprimed reference frame minus the speed of the moving reference frame. And so we can use that formula to translate this. So if the train is moving 10 meters per second, the ball on the tracks in the non-moving reference frame is going 1 meter per second, and the guy on the train will see 10 minus 1, or 9 meters per second. Back to lecture 4, titled More Rates of Change, Acceleration. Now this one is often tricky for students to grasp. It is completely analogous to the rate of change, velocity, and speed that we talked about in lecture 3. However, this is the rate of change of a rate. And I think that what makes it a lot easier to get initially is if we do a couple of things. Number one, we're going to give velocity its own unit name, just for a temporary placeholder. We'll revert back to the standard way of saying meters per second or miles per hour later on. But for now, I want to call them zips. Right, so let's define one zip to be equal to 1 meter per second. And the acceleration is the rate of change of velocity. So I'm going to write this down. Acceleration is equal to delta v, which is just measure a final velocity, measure an initial velocity, take the difference between them. That's the delta v, the change in the velocity, divided by the time interval over which that occurs. So t sub f minus t sub I, and that will be our acceleration. And so I could say, for example, that I had an acceleration, I measured, let me just draw a velocity versus time curve here, velocity versus time, and let us say that at 1 second we observe a velocity of 1 zip, I'll put a z for zip. And then at 2 seconds, we measured a velocity of 2 zips. So you can see that again we have a nice straight line. That's a constant velocity. Excuse me, it's not a constant velocity, it's a constant acceleration. And so our velocity is increasing linear in time. And how quickly is it doing that? Well, if we take our final velocity, which was 2 zips, and we subtract our initial velocity, which let's say was 0 zips, and divide that by the time interval, delta t, which is 2 seconds minus 0 seconds, then we get 2 minus 0 is 2 zips, divided by 2 minus 0 is 2 seconds, which is 1 zip per second. So that's our rate of change, or our acceleration, which means that every second we are attaining 1 more zip than we had before. Now, I'm going to just change this. Let's change this from seconds to minutes. This was the second change that I wanted to make, because I think it makes it a little bit easier when we get rid of the zips and we go back to, I'll put MIN for minute, because if I just put M, it will look like meters. Minute, there we go, here as well. I guess I could have used hours, but that would have been easier. All right, so our time, which we're measuring in minutes, this tells us that we attain 1 more zip every minute. But I'm going to keep what a zip is as still 1 meter per second. So if I now get rid of the zips, what is my acceleration? Well, 1 zip is 1 meter per second. So I'll still have 1 zip, which is 1 meter per second per minute. Which means that after 2 minutes, I would have attained an additional 2 meters per second. After 3 minutes, I would attain another 3 meters per second. Pretty straightforward. Where people get confused with this is that if I now, instead of using minutes, I use seconds, what happens? Well, there are 60 minutes in, 60 seconds in a minute, so this would be 1 meter per second divided by 60 seconds, which is, we're just going to make this as 1 over 60 meters per second times 1 over seconds. Well, that's 1 over second squared. And so acceleration in SI units has meters per second squared, and that can be confusing. Another way to say it, you could say 1/60th meters per second per second. That would remind you that the rate of change is a rate of change of a rate itself, which is velocity, which is meters per second. So it's meters per second per second. And that essentially is what acceleration. We can say the same things about average acceleration and instantaneous acceleration that we did when we talked about velocity. All of that ports over directly to acceleration. And I think that's it for acceleration. Welcome back to lecture 5, titled Constant Acceleration in One Dimension. So you'll recall that the definition that we had for the average velocity was just the displacement divided by the time interval, or delta x over delta t. where delta x means x minus some initial x value. Now, some people would write x sub f minus x sub I for final position minus initial position. I tend to like to use x naught for our initial position, and that's what x naught means here, and also t naught means our initial time. Usually we take that to be 0. It means our ruler is lined up with 0, so x naught is 0. All right, now, I also want to consider a constant acceleration. And recall that if we have a constant acceleration, that means that every minute we're going to get an additional bit of velocity. So it could be that we get an extra meter per second of velocity. It could be we get an extra mile per hour of velocity. Or we could get another zip, using the terminology we used in the last lecture, per second. So if we have a constant acceleration, then our velocity will be linear, right? We start out at 0, and we have an acceleration of, say, 1 meter per second squared, and that's 1 meter per second. Then after 1 second, we're going 1 meter per second. After 2 seconds, we're going 2 meters per second. After 10 seconds, we're going 10 meters per second. That's what it means. And we talked previously about the instantaneous velocity versus the average velocity, and I said that you can get an instantaneous velocity by taking a smaller interval, right? So instead of thinking, well, what's the average velocity starting at t equals 0 all the way to some time t, down here. Instead, we could say, well, let's consider an interval around this point here. And I'm going to take the average. So it's a little bit of a later time and a little bit of an earlier time. So at this point, my velocity would be something we might call v naught. And at a later time, it would be v naught plus the acceleration times the time. Because after the time interval, delta t, going from here to here, so this is t naught, by the way. Should write that, t naught. So this interval here is the delta t, which I'm going to define t naught to be 0, so we can just call this t. The constant acceleration we're experiencing, we just have to multiply that times the time and add it to our initial velocity. That's a special case for constant acceleration only. And if I do that, I can average these 2 points. Okay, I keep saying average velocity, but I haven't actually shown you an average yet. So let's make this into an average. Well, how do we average 2 things? We add them together. So I'll take v of t plus v naught, and I'm going to divide it by 2. Because there's 2 things I'm averaging. And so what do I get? I plug in for v of t, which is v naught plus at plus v naught divided by 2. And just so you know, a little bit of algebra, we get that this is 2v naught plus at divided by 2, which is going to be equal to v naught plus 1/2 at. Now I'm going to use that. I'm going to write this equation and call it equation 2. And I'm going to note here that t naught is equal to 0, right? Therefore, delta t and t naught are the same thing because delta t is t minus t naught. If t naught is 0, then delta t is just equal to t. And now I want to use this definition of average velocity with this equation that I have here that resulted from taking an actual average. And here's how I'm going to do it. I'm going to say delta x over delta t is equal to this average velocity, v naught plus 1/2 at. Now, I said before that t naught was 0, so delta t is really just t, right? When I multiply both sides by t, giving me that delta x will be equal to v naught plus 1/2 at, all times t. So that's just saying that the distance traveled is the velocity times the time. Now all I have to do is distribute this t and do a little bit of algebra. Delta x equals v naught times t plus 1/2 a times t squared. Now delta x, you'll recall, is just x of t minus x naught. And that's equal to v naught t plus 1/2 a t squared. I'm going to solve this for just x of t. And so why am I doing that? Well, that gives me an equation that's a function of time that gives me the position in terms of the initial position, x naught, the initial velocity, and the constant acceleration that we're experiencing. Now, keep in mind, this only works, this 1/2 at squared term at the end here, only works if we have a constant acceleration. It would be different if we had some other time variation for the acceleration. And so this we'll call equation number 3. That's what we wanted to get. And this is the basic equation we can solve lots of physics problems with. For example, we can say if we start at 5 meters from some reference frame, traveling with an initial velocity of 10 meters per second, and we travel for 3 seconds under an acceleration of, a, where a is some constant value, then how far have we traveled? Well, we can ask other questions too. We can say if we've traveled, some distance, x of t minus x naught can be our delta x, and so we travel 10 meters with an initial velocity of a meter per second and an acceleration of a. How long does it take to travel that distance? And we can solve for t in that case to get that answer. So there's lots of things we can do with this equation, and in the next lecture we'll talk about a special case where we can manipulate this and solve for the time it takes to fall from a tree, for example. So why is this useful? Well, because we'll find out later that, that the gravitational acceleration near the surface of the Earth is approximately a constant. And so we can use a constant value to calculate things related to falling objects near the surface of the Earth. We'll turn the a into a little g, and we'll say that g is equal to either 10 meters per second. If we were to be more accurate, we might say 9.8 meters per second. If we want to use different units, we might say it's 32 feet per second. But that's the acceleration that you experience near the surface of the Earth, and it's a constant acceleration, approximately. Welcome back to Lecture 6. This lecture is titled, How Fast? And so in this lecture, we're going to imagine that we drop a ball from some high distance, like say a tree in your backyard. And we want to know if it falls some distance, delta x, or really displacement, delta x, how fast is it going right before it hits the ground? Normally the way we would do this is a two-step way, but what we're going to do is derive an expression which allows us to get that velocity given this displacement, delta x. And so how we're going to do that is we're going to use two of the equations from the last lecture. This first equation is just for the velocity as a function of time. I should really write this as a function of time here. V of t is equal to an initial velocity plus g times t, where g is the constant acceleration we experience here on Earth, 10 meters per second. And so the first thing I'm going to do is I'm going to rewrite equation 1 as v of t minus v naught equals gt. And v of t minus v naught we're going to call delta v. That's just our change in velocity. And then I'm going to solve. Then I'm going to solve for time to see how long it takes to fall. And so doing that, just a little bit of algebra, we get that this time is equal to delta v divided by g. Now we're going to substitute this time value into equation 2. And so substituting 1 into 2, we find that x of t is equal to x naught plus v naught times t, but t is delta v over g, plus 1/2 g t squared. But again, t squared will be delta v squared over g squared, Now we're going to simplify it a little bit. I'm going to take x of t and subtract from both sides of this equation x naught, so I get delta x, because remember that delta x is equal to x of t minus x naught, which is going to be just equal to v naught times delta v, but now I'm going to substitute in for delta v, v of t minus v naught, divided by g, plus 1/2. I'm going to simplify the g's here. We've got g times 1 over g squared is going to give us 1 over g. So that's delta v squared, but we're going to write that as v of t minus v naught quantity squared all over g. All right, the next thing I'm going to do is I'm going to multiply both sides by 2g. Doing so will cancel this half here, but it'll put a 2 on this term here. But we'll get rid of the g in the denominator of both of these terms. And so I'll get that 2g times delta x is equal to v naught times v of t, which is v naught times v of t, minus v naught squared. And both of these are times 2, so I'll put a 2 in front of both of them. There we go. Plus, now I've got to square this term out. So it'll be a v of t squared Then we'll have v of t times v naught, or minus v naught, and then also minus v naught times v of t, so that'll be minus 2 v naught v of t. And finally, minus v naught squared is going to be plus v naught squared. And if we look at this, we see that we've got a 2 v naught v of t and a minus 2 naught v of t right here. Those will cancel out. And we'll be left with 2g delta x is equal to minus, well, let's do it this way. Let's do it v naught squared minus 2 times v naught squared. And I think that is close to what I want. Let me just check something. Do I have a factor of 2 out of place? Yes, I do. Where did I get this factor of 2? Oh, I'm sorry. I haven't finished this yet. Plus v of t squared. And v naught squared minus 2 v naught squared is just minus v naught squared. So I'll get v as a function of t squared minus v naught squared. And this is equal to 2g delta x. And so now I can solve a problem like I was talking about before. I said it was 30 feet. So let's use feet per second for our acceleration. And the gravitational acceleration in that case is 32 feet per second per second. And if we're going to consider 30 feet, we'll let delta x be 30 feet. So we'll have 2 times 32 times 30 feet times 30 equals v squared is what we're solving for. And let's let v naught squared be equal to 0. So it's falling from initially at rest. So it has an initial velocity of 0. So now all I have to do is solve this equation. So I do 2 times 32 is 64, and then times 30 equals v squared. We can do this problem here. 1800 plus 120, so that's 1820. And the units on that are going to be, feet times feet per second squared. So that's feet squared per second squared. So this will be in feet per second. So if I take the square root of both sides, I will get that v is equal to the square root of 1820. 1600 would be 40 meters per second. So if we punch this into the calculator, we can get an exact evaluation of that. Oh, you know what? Not 1820, 1920. I had to add 120 to that, and I forgot. Oh, that was great. 1920. Okay, so little math error there. It happens. So 1920, the square root of that is 43.8. So that's 43.8 feet per second.